It's such an honor to be part of the C&EN Talented 12 cohort. I just 1 second to figure out my window here. Yeah, what a fantastic symposium so far. This is a phenomenal platform to showcase the hard work, creativity, and passion of our research group members who really make our vision possible. And so there are lots of people to thank, of course, my research group, the University of Washington and the C&EN team, but also the amazing behind the curtains nominators and supporters who constantly create opportunities for me, including my fantastic colleagues at the University of Washington. Today, I'll share a research vignette that illustrates our molecular approach to synthesize catalytically active sites, which enable atomistic insights into understanding and harnessing metal support cooperativity for catalyst development. But before I do that, I want to share just a few words about my scientific journey, which was marked by amazing people and phenomenal mentors who not only challenged and helped me expand my knowledge, but also shaped my approach to science and life in general. So I'm originally Romanian, and when I was 19, I took my first flight ever to travel to Los Angeles and attend Caltech for my undergraduate studies. And as a first-generation college graduate, I can report firsthand on the amazingly positive impact that this fellowship had on my life and those near me. So I've met the most incredible people there, many of whom continue to be mentors and friends, among them my undergraduate thesis advisor, Teo Agapie. And following my undergraduate work, I pursued my PhD under the guidance of Kit Cummins at MIT, whose mentorship truly ensured my transformation into a scientist, and he continues to have an outsized impact on my approach to science. I then joined Colin Nuckolls at Columbia for a postdoctoral stint, which exposed me to new scientific areas and ideas, and these were critical to my current research program. So in 2017, I started my independent career at the University of Washington, where I am working with this fantastic team of students. Okay, so now let's get back to the science. In my group, we are interested in developing catalysts that address multi-electron small molecule transformation sequences like those illustrated on the screen. And our distinctive approach is to bring molecular level control into synthesizing the active sites, and in particular, those that harness metal support interactions in the resulting platforms. So if we consider a typical, catalytic heterogeneous surface, we find that not all of the exposed sites are catalytically active, typically. The concept of active sites was introduced about 100 years ago by Taylor, and it reflects experimental evidence that many catalytic surfaces are not uniformly active. And so they exhibit activity at sites that are distinguished by special coordination environments, typically low coordination. And so, however, in typical catalysts, we find that there are a multitude of ill-defined and varied active sites, and this can be detrimental to their selectivity, for example. And so if we are to achieve structural fidelity across the active sites, an orthogonal strategy is to synthesize single-site catalysts essentially by anchoring metal centers onto supports. And in my group, we are interested in those supports that are chemically non-innocent and therefore can work synergistically with the metal to amplify its activity. Now, if we could synthesize such single-site catalysts with high structural fidelity. And if we could experimentally probe the metal support interaction or interface with atomic detail, then we could elucidate how factors underpinning this cooperativity, for example, metal support interactions, interadsorbate effects, surface restructuring, etc., can impact catalysis and use this knowledge to tune the resulting platforms. And I just want to highlight one such effect that has captured our attention over the past couple of years, and something that emerged from our research, and which is the role of interadsorbate effects in altering activity at chemically identical neighboring sites. So how a binding event at one metal affects that of the neighbor in a catalytic context, and perhaps beyond. So in our group, we take two different approaches to make this vision come to life. So on one hand, we anchor atomically defined metals onto a heterogeneous but well-defined surface, the van der Waals surface of black phosphorus, which is on the right side of the screen. But in an orthogonal approach, we also take a more molecular path by creating these atomically precise clusters that encompass some complexities of a surface, and that importantly feature these three edge sites, or also active sites on their surface. And I'll tell you a little bit about that now. So these clusters, again, have an edge, three in fact, and these are really critical to their activity. Let me tell you a little bit about how we prepare them, because this is really central to a lot of the work we've done this far in the group. So we came up with this very versatile synthesis of the clusters, essentially taking well-known, in this particular case, 6-8 Chevreul-type clusters. So this octahedron of metals, in this case cobalt, encased in a cube of chalcogens, deliberately selected to be seleniums in this case, and appended on their surface ligands that can support the secondary coordination environment. And this is important because these coordination environments can support metals on the surface. And so projected down the C3 axis of this cube on the right side of the equation, you can see this nanopropeller-shaped molecular cluster that emerges, which features three metals of our choice, pretty much on the surface. And again, this is a modular and very scalable synthesis, and enabled us to do a lot of chemistry around understanding the metal support cooperativity. So I'm highlighting on the edge, on the right side, the edge itself, because this is really central to the reactivity of the clusters. And so let's take a closer look at it. The edges are emulating these active sites that I mentioned previously, which are known to have this, oftentimes to have a low coordination environment at the metal. And so if we highlight on a single edge site on this otherwise complex cluster, and so I selected here the cluster that has iron on the surface, we can observe this hemulability of the edges and understand a little bit better that cooperativity. So for example, in the neutral state, a tri-iron cluster, again focusing on a single edge site using single crystal X-ray diffraction, we can see that the metal engages with an external ligand, in this case isocyanide, and a single of the two possible seleniums exposed in this coordination pocket. Now, by simply changing the oxidation state of the overall cluster, so for example, by reducing it on the left side of the equation, we can see that the selenium atoms become so electron rich that they outcompete the exogenous ligands. And now the metal is engaged with two of the two possible seleniums on the cluster surface. And the opposite happens upon oxidation. The cluster completely, the iron completely disengages from the cluster surface upon oxidation. And exogenous ligands like this phenanthroline can just coordinate and outcompete the seleniums. Another thing that can really change the strength of this metal support interaction is the metal identity itself. And we looked in great detail to understand this, but this is really to showcase the flexibility of this cluster support as a ligand framework, essentially. So going from chromium to zinc, we can observe the surface of the cluster restructuring slightly and to accommodate the preferences of different metals. So for chromium, you have the square pyramidal coordination environment with an external ligand bound. Most of the metal edges, like iron, manganese, etc., have a pseudotetrahedral coordination environment. And then here's copper, which adopts a linear one, really a result of charge transfer with a cluster. So this atomistic understanding into the metal support interaction, both structurally and electronically, has enabled us to really address more complex questions. And this is the one that I want to highlight now in this little story. And if we consider now the cluster as a whole, we find that at least in a first approximation, there are 3 chemically identical active sites or edges on this cluster. So we asked a simple question: can we capture the effect that a ligand binding event at one such edge site has on a neighboring one? And does it alter reactivity, or do they just behave similarly or identically? And so to tell this story, I chose this trichromium cluster. Again, the same there's a lot of structural complexity there, but this is our nanocluster with 3 edge sites, which are chromium now. And we chose this because this provides a nice redox-independent regime between the metal and the support. And studied in some detail a reaction that we use to benchmark our clusters, which is this azide activation and transferring of a nitrene group to form carbodiamide. These clusters are fantastic catalysts for this transformation, but what I really want to show you is that we can really gain atomistic detail into how these 3 edge sites work together to facilitate this transformation. So in stoichiometric conditions, John Kephart, who led this research project, found that he can actually isolate all the key catalytically competent intermediates within this transformation. So treating the cluster with 1, 2, and 3 azide equivalents provides these intermediates, which can be isolated and studied in great detail, and then sequentially we can add isocyanide to transfer the nitrene, revealing the original chromium 2 sites on the cluster surface. And so single crystal diffraction is really a fantastic way to gain these atomistic insights onto the clusters, and they enabled us to understand and almost get a frame-by-frame movie into how the transformation occurs at the single edge site. Okay, so on the there's an inset at the bottom which highlights only a single edge site and on these complex structures, and that's the ones that I would like to draw your attention to. So if we start off with this chromium 2 edge site that binds a pyridine to it, upon azide activation, we can move to the next structure to the right. We can observe the chromium has changed its coordination quite drastically to accommodate chelation at this tosyl nitrene group. Finally, the isocyanide comes in and binds at this chromium edge site, releasing the oxygen that was previously chelating at the chromium. And this is actually a snapshot in the resting state of the catalyst also. It's kind of cool. This edge site doesn't directly spit out the product, even if both substrates are bound to it. But then we think a second equivalent of the isocyanide comes in to finally release this chromium 2 site bound to an L-type ligand. And of course, the final product. But the question, although it was really great to see directly that all of the edge sites are in fact catalytically competent active sites, the question that really is on our mind is, are all of these edge sites acting the same way? Now, if we, at a single edge site, we can envision how this transformation occurs. But, if we consider all three at the same time, there's a lot of complexity that emerges. And so into sequentially activating the azide and then transferring it to the product, to form the product and reveal the chromium-2 sites in the process. I want to highlight, though, two of these species that really enabled us to probe this question. We can, as I mentioned previously, isolate these catalytically competent intermediates at scale. And so on the top left, we could isolate and characterize in the solid state this tris-imido cluster. So each chromium is engaged with this imido group on the surface. There's some interesting stereochemistry going on there that I won't get into, but on the right side, we can also isolate a similar related cluster that features only a single chromium imido on the cluster surface, whereas two of the three chromium edges are now engaged only with isocyanide, right? So this enables us to make a direct comparison in the reactivity of these two species. If there's no connection between them, then between the active sites, then they should react the same. But that's not what we find. It turns out that the tris-imido cluster has a significant affinity for isocyanide to bind and give rise to this, the steady state form of the catalyst. But in contrast, the monoimido cluster actually has very, very little affinity at this chromium imido edge site for the isocyanide. So what happens at these neighboring sites truly impacts reactivity at the neighboring one. And this inorganic cluster support is essential to communicate that information propagate the information from one edge to another. And in many ways, what we observe here is really similar to these interadsorbate interactions that occur on many surfaces, for example, iron sulfide, that lead to coverage-dependent adsorption of substrates. And so we can capture this in a molecular system, but with atomistic insights. And so just to conclude, I want to show you one of the ways in which we think that this allostericity essentially that occurs on the surface of the cluster can be harnessed for various purposes. And so we think a lot about that in the group, but just one recent way in which we've collected on this is to seed the synthesis of these programmable or stimuli responsive materials. So the clusters themselves actually are fantastic building blocks for materials, and we are exploring that in the group. But here's a way in which this allostericity was enabled us to really use it in material synthesis. So this table of contents graphic illustrates a similar cluster. So you can see that cobalt selenide cube in green, but then on the surface, there are three initially chemically identical sites. Now, upon exposing these edge sites, which are zinc in that particular case, to ligands, it turns out that only two of them engage with ligand binding. Again, this information that gets transmitted from one edge to another, altering reactivity of the neighboring edge sites. And so because only two of these edge sites engage with ligands, we harness that to prepare dimensionally controlled or pre-programmed materials like wires. And on the left is a skeleton of a structure of such a wire. The cool thing is that by taking advantage of the chemical non-innocence of the support and oxidizing it, we actually can turn on selectively a single one of the coordination of a single site on the cluster surface, turning this into a tritopic building block that can enable the synthesis of two-dimensional van der Waals nanosheets, and that's what's depicted on the right side of the slide. And so I think these kind of stimuli responsive materials are something that we think about a lot, especially intertwining it with catalysis. So I'll conclude my my little vignette, research vignette, and but not before I acknowledge all the group members, current and former, who have really just been a fantastic crew to work with, the funding agencies, essential, but also our wonderful collaborators without whom we would not have been able to realize a lot of aspects of our research. So thanks everyone.
Thank you, Alexandra. I wanted to ask, what do you think the stimuli responsive materials you showed at the end will be used for?
Well, that is a very good question. I think that it's really aspirational at this point in time. You know, programming materials, both structurally and functionally, could have implications in many fields. We are really at the root of that on the more fundamental aspects of understanding the processes rather than collecting functionally. But I am most excited about bringing them into regulating catalysis and creating, cascading processes that could occur on the cluster and work synergistically to tackle these really challenging multi-electron transformations of small molecules.
All right. Thank you very much.